Welcome to Inference with Two Proportions. We dive into Chapter 12. Deep into Chapter 12, we're going to take a look at number 35, which is on page 719 in your book, if you'd like to follow along. I have written just a nice little summary of the problem here. Do drivers reduce their excessive speed when they encounter police radar? And that's open to interpretation. I'm sure there's some details here. What is reduce excessive speed? Does that mean slow down to the speed limit, or just a 10 over and they were doing 20 over? Encounter is a little bit of a vague word. Does that mean they see a sign, they see a police officer, they have radar detectors? But in any event, it's a study on the effect of radar on speeding. And we do have two groups of people here. We have a large group, almost 13,000 drivers with no radar visibly present. By the way, they're all being tracked by some secret, invisible speed detection mechanism under the pavement. And the second group, there is visible radar. But Part A is actually from kind of a 12.1 kind of problem, because it is just asking about one group, so it is a one sample. So let's move to that. So right now we're going to ignore this group and just look at the no radar group. So I've written over here the p hat, that is the sample proportion. And notice they have not given us proportions. Sometimes in these problems they will give you a percentage. And you'll find out, and your calculator actually is looking for a number of successes. This is a little bit backwards, but here's the number of successes, right? We're looking for speeders out of a possible number. So we observed almost 13,000 drivers, and 5,690 of them were going over 65. So some definition of speeding. So that's 44%, and now we're being asked to find the 95% confidence interval. So what does that mean? We have a point estimate. It's 44%. But how good is that? Well, I'm telling you, that's a lot of observations. So that's a pretty good, nice, steep, normal curve. And we are dealing with Z distribution, good old normal distribution, Z scores, because even though sigma from the population is not actually known, we can calculate it with proportion problems. Given the three assumptions, I'll just write them down real quick. What are the assumptions that, or the criteria that need to be met? First of all, we have to know that our sample size is not too much of the population. That is, the total population has to be at least 10 times bigger than the sample size. Or another way to put it is your sample can't be more than 1/10 of your population. And then you can't have too few successes, too few failures. Otherwise you get a very skewed binomial looking, like if you had a 90% free throw rate, what would your graph look like? It'd be like, yeah, we never expect you to make 0, 1, or 2, and we often expect you to make 8, 9, or 10. So that's my attempt at drawing a binomial graph skewed to the left. So to avoid that kind of situation, we have this rule where n times p has to be at least 10. 10 seems to be the magic number here. Also, the failures need to be at least 10. Well, those are all quite nicely met here, so we're using this curve with nice z-scores. The z-score, of course, the critical value here is good old 1.96. And if we were doing this by hand, we'd need to know that, right? There'd be 2.5% on this, 2.5% on this. But I think we've reached the point where we are going to rely on our calculator. I just need you to understand a couple things about what's happening with the variance. And otherwise, we'll just let the machine do the work here. So let's see. I think we're ready. Let's switch over to our calculator. We are using stat tests, and then there's quite a variety here. So the hardest part of doing these problems might actually be choosing the right thing off the menu. These first 6 are all for means and significance tests. If it says test, that means a test of significance. We're actually looking for a confidence interval, and these first 2, 7 and 8, are for interval estimates of means. Then we get 2 sample estimates of means, and finally when you start to see the proportion ones, and for part A here we just have one proportion, z interval. And so we put in our x, we put in our n, just make sure you don't switch those two, you'll get an error. Put in the right confidence level. And maybe we could just go back just for a second and look, why are we using these numbers? What is a confidence interval? It is the point estimate, not x bar anymore, this is p hat, a proportion that's come from a sample, plus or minus our critical value, times an estimate of standard deviation. In this case, we have our old friend P times Q divided by N. Well, what does your calculator need? For the z-score, it needs that confidence level, so you have to tell it 95%. And then for the everything else in here, the P is coming, maybe I'll just draw it up here, P hat is coming from your X and your N. P, oh, by the way, these are P hat and Q hat. These are also coming from here. So we're just telling our calculator 3 numbers. Let's go back to that. These 3 numbers, and it can do all the work for us. So there we have it, 431 and a 449. 431 and 449. So what is that margin of error? This margin of error has been calculated for us. This is 44% plus or minus 1.9% or 0.019. And that's often how that would be reported in the news. 44% plus or minus 2%. In other words, between 43 and 45%. We are 95% sure that that interval captures the true proportion of speeders, which, when you think about it, is probably pretty high and pretty accurate. Now, what about the interest of the study here? We are now looking at 2 samples, both of these, and we are interested in the effect. So what does that mean? We're really looking at the difference. What difference does radar presence make? That's what we mean by the effect. So, no radar, kind of the control, right? Then we show maybe a sign or some cop cars standing out. I don't know, maybe it's a cardboard cutout of a policeman with a radar gun in his hand, something where a driver is encountering radar. What does that do to their, as a group, what percent is now speeding? Well, and I've switched these so that this comes out as a negative number because it is a reduction in speeding, right? So that's the point estimate of the effect. What effect does radar presence have? It reduces speeding down 12%. A 12% reduction. So we'll put that as a negative number. But what kind of confidence interval? These again are, it's a 95% confidence interval, so these numbers don't change in the calculation. We're going to tell our calculator the same thing, 95% confidence level. But what is different is that we have a difference of means, average proportions, these are. And then we have an adding. That's kind of the big point here, that we add variances. I mean, you already know this, but now we're just seeing it in this formula. I guess this would be R. That's supposed to be an R, QR. and R. And then over here, this is a different proportion. Of course, the textbook does not use Q, but that's 1 minus P. And so you have a variance here. You're adding to the other variance. This has much more variance, and then you take the square root of that. Well, our calculator can handle that. We're just giving it 5 numbers now. We're giving it the 2 x's. We're giving it all 4 numbers up here. The what are these? The 2 x's and the 2 n's, and then finally our 95% confidence interval. I'll switch back to the calculator. Again, tough part, choosing from the menu. Tests. Remember, it's not actually a test of significance here. We're doing an interval, so start at number 7. If it just says Z or T without a prop, then we're talking about mean estimates of a mean. So we're looking for PROP for proportion, and now we have 2 proportions, 2 proportion intervals. So we're going to choose B there on this list at least. I've put in the, oh, I can do this. This is actually 1051, and this is 3285. This should be 5690, and the number of cars was 12,931. 95. So there's our 5 numbers input. The calculator will do all that fancy math for us. And let me point out something that had we, let me put this in a different color just for a second here. Had we gotten a positive number over here, this would act as a significance test, because the null hypothesis would be that the difference is 0. There's no news here. Your suspicion is wrong. The program's not working. There's no effect. And what would a confidence interval, I don't know what this would be. Would this be something like -27 or something? Well, the fact that 0 lies within your confidence interval makes it inadvisable, impossible, not recommended to reject the null hypothesis. The null hypothesis says it's 0. 0's inside the interval, so your mean might be 0. There might be no difference. Now that is not the case, but that's how you can use a confidence interval as a significance test. Actually test those hypotheses with a confidence interval. Well, we know that this is quite negative, that 0 does not lie in this interval. And there's our result there. I'll switch back to yellow here. I don't like that red. And this was a low. So the lowest we suspect the true proportion is 10.2% that it went down, and possibly improved it by even 13.8%. Okay, so that's a margin of error of plus or minus 1.8%. How do we phrase this in English? That's an important part. There's a 95% chance that our interval captures the true proportion. It's not a 95% chance that the true proportion is going to land somewhere. There's a 100% chance that the real proportion is what it is. But our interval is a little bit iffy. You know, we could miss, but we're 95% confident that we have captured the true proportion of, in this case, the difference in the proportions of speeders given a presence of radar. There's one last follow-up question, and that is, how would clusters of cars make our inference invalid? This study was done on a rural highway where it's much more likely to just get one car at a time, maybe one car per minute going by. What if you had clusters of 5, 7, 10 cars, and you know, if the guy in front, the first couple cars in front slow down, and obviously the other 5, 6 cars behind them are going to slow down. Well, we have these 3 assumptions that make inferences valid, And we would be, if I just may go back to that, it is red, and we would lose our independence, right? Because one subject in the study would be influencing the behavior and the results of another. Okay, well, that's it for number 35. Good luck with your assignment.